Alright, we're going to practice another decay. The trick with beta is that you also have to include the neutrino or antineutrino when you're dealing with beta decay. When you're dealing with beta negative decay, or where you're kicking out an electron, that's always going to mean that you're going to have a antineutrino. So electrons correspond to antineutrinos. So when I write this, I have to deal with conservation of energy and conservation of momentum, and that neutrino is there to balance that equation. I'm not allowed to break the loss. Even though the mass of a neutrino is insignificant, there is a tiny little bit of mass, which if it's moving very fast, has a significant amount of momentum. It's there to balance that energy. It's there to balance the momentum in this equation. You will balance the total nucleons and you will balance the charge without the neutrino or antineutrino. You just stick this on at the end, and all beta have this. So calcium 46, calcium is element number 20 on the periodic table. So calcium 46, 20 protons, is undergoing negative beta decay. So we have a beta particle, 0, -1. And now we balance, well, since we have no change in nucleons, that should leave us with still 46. A -1 now means we have to have 21 protons. Element number 21 on the periodic table is scandium, Sc. And then to balance the energy and momentum, we stick in an antineutrino, which is given by the symbol V with a line above. Its mass and charge is 0 on here. You can put this 0, 0 if you want, or you can leave it out. That doesn't matter. We assume that the mass relative to the rest of these particles is insignificant. Its charge relative to these particles, insignificant. So that's why we put 0, 0. The mass of a neutrino or antineutrino is not really 0. It's just so small in comparison to the other particles, it doesn't affect our calculations. But this needs to be added on our decay equations. Every time you have a negative beta decay or an electron being emitted, an antineutrino will be emitted as well. One thing to note, negative beta decay, kicking out electrons, is the most common type of decay. We know there's two where an electron and the other one's a positron gets emitted, which you'll see in example 3. But negative beta decay is the more common type that occurs naturally. Electrons occur naturally. Positrons have only been created in particle accelerators. They're not a very stable particle. Therefore, they tend to disintegrate very quickly. So they only exist for very short periods of time, where this reaction can occur naturally.